Hi there, I've not made a video for a while, so I've decided to do some multiple choice questions. I'm going to start with some further mechanics from A2. So the idea is I will show you the questions. You can have a go at the questions. I'll put the answers on, then you can mark it. Then I'll do the ideal solutions for each question. So obviously my advice would be to attempt the questions, check the answers, and then specifically look at the questions which you didn't get right. And if there's any questions where you kind of guessed it or you're not quite sure, maybe look at the explanation of that one as well, because it may help. All right. So I'll go for the questions. So just pause for each one, attempt it, and then we can mark it afterwards. So this is the first one, and the next one. So this is number 2. So pause to have a go, and then the next one. So this is question 3. As you can see, it's a decent mix of questions, different types. So let's look at number 4. Number 7, a bit of a weirdy one. Obviously we don't like these, that's why we've done physics, but we've got to do them. Number 8, and we've just got a few more. Finish with 9 and 10. So once you've done those, I'm going to put the answers on, mark the work, and then any that you obviously get incorrect, I'm going to take you through all the solutions now. So they're the answers. If you want to pause and mark them, and then any that you've got wrong, just flick forward, or any that you're not entirely sure on, and I'll explain them. So these questions are quite common across all exam boards and can be quite complicated, but once you've done a few examples, it should be okay. So the first thing that you need to do is to identify the forces. So these types of questions work when something is spun in a vertical circle. So let's go for the labeling of the diagram. So we've got a mass here, so obviously the weight, which is mg, will act downwards. You've got the tension, which from the string, which will act towards the centre of the circle. And then you've got the centripetal force, which always acts towards the centre of the circle, so up. So I'm going to put, it could be mv squared over r, which is the centripetal force, but in this case I'm going to go for mr omega squared, and you'll see why shortly. So to answer a question like this, we need to do the sum of the forces is equal to the centripetal force, which could be mv squared over r, or in this case mr omega squared. And remember, omega is the angular velocity or the angular frequency, and it's measured in hertz or cycles per second or revolutions per second. Now in this question we've got 120 revolutions per minute, so we can get that into seconds by dividing by 60. So 120 revolutions divided by 60 gives us 2 cycles per second, or 2 hertz. And what we can do now is use the angular velocity, 2 pi f, so you should have done that when you did circular motion. And then it's just 2 pi times the frequency, so the frequency is 2 hertz, so we've got 2 pi times 2. So 2 pi times 2 is obviously 4 pi radians per second. And then we just sum the forces. So we'll take up as positive because that's the direction of the centripetal force. So the sum of the forces will be T, as that acts towards the centre, minus the weight because that acts in the opposite direction. So T minus mg is equal to the centripetal force, which is mr omega squared. So now it's just a matter of a bit of rearranging and putting some numbers in. So the tension is equal to, so it's mr omega squared plus mg. We can factorise that one. So tension is equal to m r omega squared plus gravitational field strength. So let's do the numbers. So the mass is 0.5. Brackets, so radius is 0.45. times omega squared. Omega is 4 pi, so omega squared would be 4 squared is 16, so 16 pi squared times 16 pi squared plus gravitational field strength is obviously 9.81. Close that up, put that in your calculator. And that should give you 40.4 newtons, which is two significant figures, 40 newtons, so that would be an answer of D. So hopefully that one's okay. And if you need it for the top of the circle, it would be the exact same, aside from the centripetal force would act downwards, the tension would act downwards towards the centre of the circle, and the weight would also act downwards. So instead of T minus mg originally, it would be T plus mg. So look at number 2 then. So this one just requires a bit of thinking. It's not very, there's no mathematics. So the easiest way to think about something like this and answer this style of question would be, so it's a simple pendulum. So it'll obviously have different locations. Just make sure that's not going to move. So, that might be a pendulum. Just going to draw it at different locations. So that's the amplitude. We've got the centre or the equilibrium position. And then maybe the amplitude on the other side. So it says, which graph best shows how the kinetic energy varies with displacement. So in the centre, or maybe let's talk about the extreme first, the amplitude. So I'll call that A. So at point A, so the pendulum's swinging out, and it's stopped and it's about to change direction. So the potential energy is a maximum. The kinetic energy is actually 0 as it's stopped to change direction. So the kinetic energy at the extreme is 0. In the centre, so as it swings on in the centre, the speed of the pendulum is its greatest. So that means that the kinetic energy is also its greatest, because obviously kinetic energy is simply half mv squared. So the faster it's going, the more kinetic energy it's got. So the kinetic energy at the equilibrium position is a maximum. So then we just need to find a graph that correlates best with that. These ones definitely not. The relationship's not linear, as you can see, kinetic energy and speed squared. So we're not going to get straight lines. It's definitely a curve, and then we just need to identify between B and C which one's correct. So at the equilibrium position, the kinetic energy is a maximum. So out of these two graphs, the one that satisfies that condition is D. So there we go. So as long as you understand this, these types of questions are quite straightforward. So let's look at the next one. Now this type of question is the exact same principle. Obviously not the same type of question, but the exact same principle as what we were looking at in question 2. So as long as you can, identify that, so it's a particle performing simple harmonic motion. So we can attribute that to the swinging pendulum, really. It's the same concept. At maximum displacement, I'll actually use the pendulum example, and we'll just pretend it's a particle. At the maximum displacement, the kinetic energy is a maximum. 0. And in the equilibrium position, the kinetic energy is a maximum. The potential energy at the extreme, at the amplitude, is maximum. And at the equilibrium position, the potential energy will be a minimum. So we'll leave it at that to start with. So let's look at, so it says which statement is not correct. So the first one, the speed of the particle is a maximum at T/4. So T/4 is this location. So displacement, equilibrium position at T/4 is, at the equilibrium position. So the speed, the kinetic energy is a maximum, therefore it's traveling its fastest. So, this one's actually correct. Next one, the potential energy of the particle is 0 at 3/4 T. So at 3/4 T, that's also the equilibrium position. The kinetic energy is maximum. Potential energy, 0. So that one's also correct. The acceleration of the particle is a maximum at T/2. So if you think about it at this point in time, for T/2, it's its maximum displacement. So when you're in maximum displacement, you've got there's a force that's pulling you in, and you're actually changing direction. So when you change it, so if you have to stop and change direction, the force applied would be its largest. And obviously F equals ma. So if you've got a large force pulling you back in, a restoring force, that would indicate that you've got your maximum acceleration. So C is correct as well. Which leads us straight into D. It says the restoring force acting on the particle is 0 at time t. Well, time t is the equivalent to time t by 2, but just in the opposite direction. And we just established that, the restoring force will be a maximum. So D is obviously not correct and must be our answer. So let's move on to the next one. So this one's just, further mechanics, circular motion. So it says a helicopter circles continuously at constant speed. We've got diameter 800 meters. Be careful, it is diameter. Normally for these equations you might use radius, so don't fall into that trap. And we've got a time of 5 minutes. It says what is the speed v and centripetal acceleration a? So speed, I imagine, is just v equals 2 pi over t. And then we just need to put some numbers in. So 2 pi times the radius, which is 400. I imagine if you actually used 800, you would get a different answer. They're called distractors. So 2 pi times the radius of 400 divided by the time period, 5 minutes. So that's just 5 times 60. Which, if my maths is correct, is 300. So put that in your calculator and that'll give you the speed. So that's 8.37, which obviously rounds to 8.4 meters per second. So that leaves us with B or C. So obviously what we need to do is establish what the acceleration is. Now the acceleration equation, we've got the speed is just v squared over r. So if you do the 8.37, which should still be in your calculator, 8.37758, etc. Let's square that quantity, and then let's divide it by the radius, again, which is 400. So if you pop that in your calculator, we get 0.175, which obviously rounds to 0.18 meters per second squared, which gives us the C. So let's have a look at the next one. Yeah, so a distractor one for this one is typically this one. This one has probably been taught to you by your teacher. However, it's not the velocity displacement. That one is, there's an equation for simple harmonic motion. Acceleration is minus omega squared x. So normally this graph well, I say normally, it is acceleration against displacement. And that's just in the form y equals mx plus c. So obviously acceleration's on the y-axis, displacement's on the x-axis, and the gradient is negative, and it's omega. So the gradient of this graph is omega squared, and it's negative. So that's just in the form y equals mx plus c. I've had students just circle this one because they've seen it before, but that is, not the case in this one. So what I advise you to do is just to learn which one this is. It's definitely not C. It's not a constant speed. It's not A because they're only positive values of velocity, and the velocity is changing direction completely from the equilibrium position. So it's impossible to be A. So it's actually B. What I advise you to do is just learn that is the velocity displacement graph. And if you see it in a multiple choice question or in a long answer question, you just know which one it is immediately, so you don't even have to think about it. So B is Vx, this one will be Ax on the right hand side. So just be careful with that one. So let's look at number 6. Yeah, this is a classic and people love getting this wrong. So you just need to know the equations really. So the equation for the mass spring is T equals 2 pi square root m over k. It's on the data sheet, well, from definitely for the AQA and the OCR. I'm not sure about other examples, I believe the same, EdXL, OCRB, etc. I just remember it's T equals 2 pi Michael Kors. I've got no idea why, it just seems to help, so I don't have to look at the data sheet. But obviously you can, that's completely up to you. And then the other one is T equals 2 pi root L over G. Then we just need to have a look and a think, really. So the mass spring system, it's a bit of a confusing one, but the mass spring system doesn't contain G. There's no gravitational field strength. So it's actually, it's constant, doesn't change. So the mass spring, no matter where you took it in the observable universe, doesn't matter what the gravitational field strength is, it still oscillate with the same time period. So it's one of these. You might think that's a bit strange. I do a question in a lesson where I give some data, and then, on the Earth, what is it? And they say, now what is it on the moon? And I reckon out of 1,000 students that I've taught, maybe 10 have ever got it correct, because they've not thought. So when you actually take to the moon, if you applied the same conditions, you'd get a different, you get a different restoring force on the mass. So, it's definitely, it's T. It doesn't change. And it's tested consistently year after year. The other one is the time period for the pendulum would change, because T is proportional to 1 over G. Well, root 1 over G, or T squared is proportional to 1 over G. So in this instance, the gravitational field strength is 4 times. So if we put a 4 there, if it was T is proportional to 1 over G, then, if that was 4 times, this would be a quarter, which is the same for the one above, but we can't put a quarter there. Excuse me for that one. We can't put a quarter there because a quarter squared is 1 over 16, which is wrong. So we need to think of a number that we can square that equals a quarter. So a number that we can square that equals a quarter is simply a half. A half squared is a half times a half, which is a quarter, but the answer is a half, so the answer is A. So B is definitely the distractor, and I imagine quite a lot of students pick B. In an exam you're in a rush, you might pick it by accident, but the answer in this instance is definitely A. So let's look at number 7. So number 7, a bit of a wordy one. Mechanical oscillator is set into motion by a periodic driving force. So that just means the easiest thing to think about would be like pushing a child on a swing. So you push the swing, and the driving force or periodic driving force will be you pushing the swing at a definitive time period. So every 2 seconds you attempt to push, even if the person is there or not, type thing. So what's correct for the system? So force vibrations occur at only particular frequencies. That don't even really make sense. That's definitely not correct. The oscillator is subject to damping only at the resonant frequency. No, it'd be subject to damping at many frequencies. It's definitely not this. When resonance occurs, the dampening force is a minimum. Well, that's backwards, because resonance occurs, there wouldn't really be a damping force. So what's correct? The oscillator will not continue to resonate when the periodic driving force is removed. Well, that's pretty obvious. So if you remove the force that's causing the motion in the first place, then obviously it can't resonate, can't do anything. It'll just it'll stop over time regardless. So it's definitely D, but I can see why that's it's a bit confusing until you actually read D, and then it's very apparent. So when you've got this type of question where it's which one's correct, make sure that you read all the responses before making a decision. Maybe you might read through it and think, yeah, this one might be right, this one's definitely this one's definitely not. Oh, it's D. So that must be wrong. I would take that approach to this type of question. So let's look at number 8. Yeah, beautiful question this. Bit of a classic. So, we've got force acting down, so that'd be mg. And the force that's, keeping this turning in a circle is the centripetal force, which is mv squared over r. And if this system, it keeps doing what it's doing and is staying in equilibrium, as it says, it travels in a horizontal circle of constant radius at constant speed, then, we'd anticipate that the two forces are balanced. So we've got the mg must equal the centripetal force. So you just write mg must equal the centripetal force, which is mv squared over r. Just redid that so you could actually read it. And then it says which of these expressions equals m. So just rearrange to find m. So mv squared divided by rg, which is C. So let's do the next 2. Now this is quite tricky, this one, in my opinion. You might have done this one. I thought, yeah, that's straightforward. But number 9, the frequency of a body moving with SHM, simple harmonic motion, is doubled. So the frequency is doubled if the amplitude remains the same, which the following is also doubled. My advice for this one, especially if you do the AQA, is to look at the equation sheet. Unless you're a genius and you can just answer it anyway. But if you're just normal, like most of us, I'd look at the equation sheet and I would look for an equation that had frequency and amplitude in it to start with, and then associated with either A, B, C, or D. So what you should come up with is, V equals, it's V equals omega A. On data sheet, I believe it's V equals 2 pi FA. So this one makes sense. So the frequency is doubled, so we could double the frequency F. The amplitude remains the same. So if that's doubled, I'm going to just change colour so I can see this one. So if I double the frequency, keep amplitude the same, which one of the following is also doubled? Well, it must be velocity. It's got to be doubled. So C, maximum velocity. That equation actually is Vmax equals, Vmax is omega A, or 2 pi FA, or Vmax is 2 pi over T times A. Either iteration. Obviously go for this one because in the question it talks about frequency and it talks about amplitude. So this is the one. So I'm just going to remove some of that. So we can look at number 10. So number 10 says particle oscillates with undamped simple harmonic motion, the acceleration of the particle. Now what you need to know for this one is, the stuff that we did in some of the first questions. If you just think about the pendulum and what happens. Now you might go to this one straight away. So the acceleration of the particle is always in the opposite direction to velocity. Well, acceleration is always towards the centre. It's always a restoring force. But the particle will have a velocity vector towards the equilibrium position when it's moving in that direction, so it's definitely not A. The extent of the particle decreases as the potential energy increases. No, the maximum potential energy, remember, is at the extremes, which is also when the acceleration is a maximum, so that's backward. Proportional to frequency, no. Is least when the speed is greatest. So the acceleration is least when the speed is greatest. Yeah. So root center, maximum kinetic energy or max velocity. Not accelerating. It's its maximum speed. It's not accelerating at all. So D is definitely correct. Typically though, if you're looking at something like that, I'd advise, maybe not speed read, maybe a speed read. Read them quite promptly. Because I think once you read D, it's quite apparent that that's the answer. Anyway, I hope you found that useful. I'm going to make some more videos, over next month, definitely. I'll pick some different topic areas and I'll do some random multiple choice questions and hopefully it'll help you understand them. So if you like the video, give it a like. I've never plugged likes before, but maybe I should. If you've got any questions, just drop me a comment and I'll try and get back to you. All right, thanks for watching. Take care.